So we've kind of hinted at this, but not all reactions just go in one direction. Many reactions are reversible, meaning they can proceed in the forward direction and they can proceed in the reverse direction. The dynamic equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. When this happens, the forward reaction and the reverse reaction are still occurring. It's dynamic. There's stuff happening, but the concentrations of reactants and products are not changing. So on the freeway, there's still cars going back and forth. But the rate of going north and the rate of going south is the same, and so the number of cars at each end isn't changing. That's what's happening in a dynamic equilibrium with a reversible reaction. As the reactants are depleted, products are formed. As the products are depleted, the reactants are formed. And so it's just this back and forth. So let's look at how this might happen again with this equation, this chemical reaction of hydrogen and iodine. So at the start, all we have is hydrogen and iodine. We don't have any product. And so the reaction rate is going to be high because we've got a lot of reactant. As this begins to react, now we've got hydrogen iodide molecules along with the hydrogen and the iodine. The reaction rate in the forward direction is going to become slower because there's fewer hydrogen and iodine particles in there to react. But we have the reverse reaction also occurring now. When we get to equilibrium, we have hydrogen iodide molecules coming apart into hydrogen and iodine, this reverse reaction, and we have the forward reaction occurring as well. So these particles are undergoing reactions, forming and destroying HI, but because they're at the same rate, if we look at the number of each of these particles over time, it doesn't change. It stays the same. Is it always the same particles? No, it's always different particles. They are still reacting. Any questions? So here we have Chronicles of Narnia meet Lord of the Rings. So here we have a fictional land. There's this river separating Narnia and Middle-earth. And originally there's a lot of people living in Narnia and almost no one in Middle-earth. So here we have high population density. It's crowded in Narnia. There's lots of space over here, and people are like, I don't like being so crowded. I need some land to farm. I'm going to go across the river to Middle-earth because there's lots of space over there. So people are going to emigrate from Narnia to Middle-earth. There's no one in Middle-earth originally to emigrate to Narnia. So that reaction doesn't happen. It's all this way at the beginning. There's nobody to come back. As more and more people move over here, and this becomes a little more crowded, some of these people say, well, you know, it wasn't so bad over there. I miss that pizza place, or I miss my friends. And so some of them move back, but there's still people moving this way as well. And so it has reached an equilibrium. People are moving to Middle-earth, people are moving to Narnia, but at the same rate, and so the populations are constant. Not necessarily the same. If Middle-earth is a more desirable location, the population will probably be higher here. Maybe the climate's nicer, right? Why are there so many people living so close together in the Bay Area? Because the weather's freaking awesome, right? I think you could live there for months and months and never break a sweat. It's nice. It's sunny. It's not hot. It's never really, really cold either. So the population here in the Central Valley is less dense because, for many reasons, people consider it less desirable. Okay, YouTube video.
Say two people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other, and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces, or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now the number of limb transfers per second forward will start high and then fall. And the number of limb transfers per second backward will start at 0 and then rise. Eventually they'll meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No. Well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. Well, we're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.
Any questions? Is that helpful? That's what I was trying to say, but they did it better.